we're here to talk about what I've referenced as Einstein's crumbs. What did Einstein do in 1905? The dude was 26 years old.
He writes a series of papers, all of which completely knock the world on its proverbial
Each
arse.
one.
Yes. He said, well, you know, what is speed? It's the distance you cover in space divided by the time elapsed. So it has to do with space and time. I mean that's a huge leap already. And he said, I'd rather that your measures of space and time are relative than give up the absolute nature of the speed of light.
Wow. So your very measuring stick changes.
Right.
Relative to the other observer.
So that you get the same answer.
So that you get the same answer.
That's
This
crazy.
is the early
I still get
1900s.
chills
Yes.
a little
Which drug
fast.
is he on?
I know.
Is it opium?
What was
Is it ether?
available?
He's not doing ketamine shots.
No. This is StarTalk. Neil deGrasse Tyson, you're a personal astrophysicist. Got with me is my co-host, Harrison Greenbaum. Harrison,
Hello.
how you doing, dude?
Good to be here.
All right.
Yeah, I'm excited.
And not your first StarTalk rodeo.
Nope, not at all.
All right.
Maybe it would be my first rodeo. I've never done a rodeo. I think I would die immediately.
That's not happening here, I promise. We're going to talk about Einstein today.
Love
You're going
it.
to help me out on that?
I've heard of him.
I need more help than that.
He married his cousin. I know that.
Every time we talk about Einstein and related subjects, we have our go-to person at large. Janna Levin. Janna, welcome back to StarTalk.
I'm always glad to be here.
You're like a regular,
It's always
practically.
fun. I know.
Because Einstein's a regular. So.
I know. I feel like I just want to hang around here all the time.
So Janna, you are the Tao Professor of Physics and Astronomy at Barnard College of Columbia University, a theoretical cosmologist. Ooh.
Yeah. I mean, I say astrophysicist these days.
Yeah, okay.
Or theoretical physicist. Only because people think cosmology is like cosmetology and stuff.
Oh, okay, right,
They
right.
wanted me to do their makeup.
I want a fancy title. Fine, I'm not a comedian. I'm a punchline engineer, specializing in ha-ha building and giggle construction.
So you're Director of Sciences at the Pioneer Works in Brooklyn, one of my favorite places.
Yeah,
This is
I
quite
know.
the juxtaposition of science, creativity, and art, and it's just we're creative people on both sides of that fence, if there really is one.
Yeah.
come together and express
Yeah, I really
themselves.
feel like Pioneer Works is a sanctuary because science is part of culture. We're not trying to hide it in something else. We're not packaging it in something else. It just exists out there, and there's a big appetite for it. People
Yes.
want to know.
And you've also written a bunch of books. I have two with me, like right now. The Black Hole Survival Guide. I mean,
It's like
It looks tiny, but it's dense, like a black hole.
spoiler alert, it does not end well.
it does not end well. I could have guessed that, I think. Yeah. So Black Hole Death Guide, not
Yes.
a Black Hole Survival
Right,
Guide.
exactly.
The book is normal size. Neil's hand is gigantic.
There's an element of truth to that. Yeah.
And my favorite book I like to pronounce, The Black Hole Blues.
I love that. That's the British cover. That's very nice.
Oh, yeah. So, I get around.
Very cool.
I get around.
Very
What's the
cool.
difference between the British and the? Is there an extra U?
Yeah.
Somewhere.
Well, right. Well, actually, they're completely different covers.
Whoa.
Yeah, they decide,
Yeah.
the different countries, they have issues with each other's
They
covers.
changed Albert Einstein's teeth to make them feel less bad.
That's what I was explaining. In one language in translation, they changed my last name.
To what?
Levinova. I think it
Whoa.
was Czech. Wow. I thought that was some serious license.
We'll help you out. We'll make it less Jewy. What?
I kind
you
of
think that's what
liked
motivated
it.
Yeah, because it made it like Italian almost.
It's just a thing. Women are Levinova.
The OVA. Okay. All right.
Yeah. It was a female thing.
So we're here to talk about what I've intermittently referenced as Einstein's crumbs. You know, when you're eating a meal that you enjoy and something spills over the edge, you don't even notice.
Sure.
Because the meal is so good. And then you walk away with your plate and other people see what's spilled off of your plate. Say, hey, that's tasty. I want that. I can work with that.
So in this analogy, the other scientists are my dog. Who comes in and is like, crumbs, this is the best. So these Nobel Prize winning scientists are Rufus.
Thank you. I had
My
not
terrier schnauzer.
thought about it just that way. Let's benchmark ourselves, Janna, to, do I pronounce this right? Annus Mirabilis,
It's Latin. I'll take it.
1905.
Yes, quite a year.
Just list
Young
for
man.
me What did Einstein do in 1905? And the dude was 26 years old
Yeah.
when this happened. Go for it.
So he writes a series of papers, all of which completely knock the world on its proverbial
Each
arse.
one.
Yes, each
on its,
one.
on its Annus, if you will.
I'm sure there's Latin for that.
On his Mirabilis Annus.
Yes,
Right.
that's
Gosh, okay,
my
so-
dating profile name.
So let's see, what are they? Photoelectric effect.
Yes. Which
The photoelectric effect was the idea that sometimes light behaved like a particle and not a wave. And so sometimes when you bombard a surface with light, it will knock it like a basketball might dislodge something from place, as opposed to accumulating energy like a wave might. And so it really was very shocking in
was that
terms
the
of...
first demonstration that light could be
I think-
also referenced as particles?
Yeah, it was the first observation, connection between theory and observation,
Gotcha.
that it is actually behaving like a particle sometimes.
Gotcha.
Very shocking, because 1800s, we thought of light as a wave, and we often still do, because it's very convenient to do so sometimes, and sometimes it's acting like a wave.
Yeah, yeah.
But here was an instance where it really acted more like you threw a basketball at something.
A really tiny basketball.
A really tiny
Which was incredible for
basketball.
Einstein to observe because basketball hadn't been invented yet.
Right, and I somehow don't see him, I don't know, jiving with the sports analogy. But anyway, so photoelectric effect, shocker.
Paper 1. Paper 2.
Paper 2, special relativity, where he...
Oh, just that.
Just that. So a lot of times, so the theory of relativity became this real colloquial thing. Everything's relative, and it became invested in society. I often say it could have been called the theory of absolutism, because what Einstein really had done is he had adhered to the absolute limit of the speed of light. He took that more seriously than anybody else was taking it at the time. In fact, people were struggling to get rid of it, this idea that the speed of light was a constant. And they were doing everything they can to dethrone that concept, which really wasn't taking
Wait,
hold.
so it's not just that it's a constant. It's that it's a constant no matter how, when, or where you measure it.
Absolutely.
You're getting the same answer.
That's right.
Even if you're moving
Right.
and the light is moving relative to you, you measure the same speed of light.
Right,
Which
which is-
doesn't exist for anything else.
That's insane. That it's
Right.
an insane
It's
concept.
crazy.
Two cars coming at each other are coming at each other faster than if one of the cars stops.
Right.
Okay, but that is not true at the speed of light. You run at the speed of light. Maybe you're running slowly. Maybe you're running near the speed of light yourself. It's still coming at you at the speed of light.
Right.
It is chilling, strange, seems
So I
impossible.
think a simpler example is I'm on the front of a train. Let's say the train goes 60 miles an hour, and I throw a ball 40 miles an hour. Can I throw that fast? Probably not. Okay.
I know I definitely can.
I think you can
5
do
miles an
anything,
hour.
Neil.
I can do anything.
I think you can
It's
do
like
anything.
I throw it 40 miles an hour in front of the train. You're standing at the platform. How fast is the ball passing you? Ding, ding, ding.
Right. Is it not adding the two up?
Yeah, yeah.
I
So it's
mean,
100 miles. an
100
hour.
miles an hour.
should be. I mean, that was
But if
common
I'm on the front of
experience.
the train,
I mean, I'm not calculating the speed. I'm worried that Neil deGrasse Tyson's on the top of a train throwing the ball, and I'm very confused.
so now I'm on the same 60 mile an hour train. And I shine a beam of light, and you measure the beam of light going by you. It is the same speed of light.
We don't add the train.
We don't add the train.
don't add the train.
That's That's
Yeah.
batshit crazy.
It is crazy.
Yeah.
And Einstein meditated on this for so long, and there's kind of a simple way to see. He said, well, you know, what is speed? It's the distance you cover in space divided by the time elapsed. So it has to do with space and time. I mean that's a huge leap already. And he said, I'd rather that your measures of space and time are relative than give up the absolute nature of the speed of light. Wow. So
so your very measuring stick changes.
changes
Right.
relative to the
so
other
that
observer.
you get the same answer.
So that you get the same answer.
That's
Yeah.
not the measure stick and your rate the time ticks. That's crazy.
I
the
mean, I
early
still get
1900s.
chills
Yes,
a little
1905.
bit.
So he's which drug
1905.
is he on?
I know.
Is it opium?
What was
Is it
available
ether?
at the time?
Ether?
He's not doing ketamine shots.
No. Okay, give me more. So that's two. Third.
Brownian motion.
Give me some Brownian motion.
So if you,
I mean, I think
Look-
that feels like a dirty topic. I don't know if that's appropriate for this.
actually, I'm not. I bet Neil knows why it was called Brownian.
There's a guy.
There's a guy who first talked about the
observed
statistical-
it, but
right.
Observed it, but
Yeah.
didn't fully understand it.
Right.
Mr.
So
Brown.
We've
Mr.
all
Brown.
observed it. So you go to a window, the dustier the house, the better. You pull the curtains aside, and you start to see all the particles move around. They don't fall like rain. They bounce around.
The dust
in the
particles.
air. The
yeah.
dust particles. And you can see the reflection of the dust in the air. You know, it's kind of a beautiful image, the sunlight hitting. reflecting off the dust
Of an
particles.
undusted apartment.
I was going to say, yeah.
Of grandma's.
My OCD is like, duh.
Clean that.
Yeah, why have you let it go so long?
But we all have had that observation, and we all know it doesn't fall like rain. So Einstein also relates this to the quantum nature of matter. He says, fundamentally, air is not a continuum. If I look at it at the microscopic level, I'm going to realize it's made up of individual molecules, and the molecules are moving randomly because they're knocking into each other. They're bouncing around. He called that Brownian motion. So they bounce around randomly because they're kind of constantly banging into each other as they move around. And it was more evidence for the quantum nature of reality in very early
In fact,
years.
I think it was one of the first supportive bits of evidence that atoms even exist.
That's right.
Because you can, in other words, you can have you use the air dust analogy, but in a liquid solution, if you have a suspended particle that's larger than the molecules themselves, the particle sort of moves around in response to the collective energy of all the particles that are around it, and you can calculate what should happen if this liquid is composed of these tiny particles. And then you only get this motion when you have atoms doing the constant
absolutely.
agitating.
And we talk
Jostling,
about
that's a better word.
We talk about the temperature in the room all the time, but what that really is the average of the thermal motions of an awful lot of particles.
Yeah.
And the statistical behavior later very well predicted by Planck. And so this was all part of that early era of starting to understand that if I look at a glass of water, it is not a continuum. If I get small enough, it is actually made up of individual molecules.
So, and there was in the fourth paper, wasn't there?
E equals MC squared.
Oh,
That's a pretty good one.
okay. Yeah, how can I forget about that one?
Which to some
That
extent...
was the whole paper. You just wrote E equals MC squared.
E equals MC
Cement.
squared.
Mic drop.
This has been a busy year.
Except they didn't have mics then. But just drop. He'd
Totally.
Find
Just,
something to drop.
A speaker. One of those.
Refrigerator drop. He was working in a patent office, right? Refining things like refrigerator coolants and refrigerator cooling mechanisms. And at the bottom drawer of his desk, he had what he called the physics department. And in the physics department, he was working on these papers between refining people's patents. And E equals MC squared is one of the most gorgeous results, obviously, most famous equation. Obviously, we all love this result. And the implications of it went so far beyond his initial motivation for thinking about it. But
that's the point of this whole
so far beyond.
episode.
I mean, it's changed the world as we know it in so many ways. But
okay, so of those four results, two of them were stapled together for the one Nobel Prize that he got.
Brownian and photoelectric.
Correct. Right?
Yeah.
And so he's got one Nobel Prize for two things that
not for E equals MC squared.
And not for E equals MC squared. Not for relativity.
Let alone general relativity, which comes 11 years later.
Right. So for me, what's intriguing is his Nobel Prize is some of the least interesting work that he's done.
Like when somebody wins a Grammy for their worst album.
Well, it was practical. It was practical. The Nobel was always very attached to verifiable results. So it was very hard for Stephen Hawking to get nominated for a Nobel Prize. It was surprising to me that even Roger Penrose not only was nominated, but was awarded the Nobel Prize because they were so theoretical. And the Nobel Prize is often awarded for things that have been verified by experiment, not a minute before.
Certainly in the day.
That's the intention.
That's correct. That's correct. Because it was the idea that if it's a theoretical result, could go with the winds.
Right.
You know.
Right.
Whereas if you anchor it in an experiment, then we got legit. You become legit. So
he did this all at 26.
By the time he turned 26,
I'm 38, so this is very demotivating.
Sorry.
I'm
what
already
is your
12
mommy
years
saying?
past.
Look at us both consoling.
Okay.
Yeah, this is
So you're 38? Okay.
38.
So when Mozart was your age, he was already dead for a year. Okay. So I don't mean to tell your mom this.
no, it's not going to happen.
You are such a disappointment.
As for Einstein's latest idea we're still chasing, CERN is building the future circular collider, a massive machine designed to explore dark matter, antimatter, and the unknown edges of physics. Ground News analysed over 100 articles covering this to pull the most credible information into one place. Depending on where you look, it's either a triumph of human curiosity or a multi-billion-dollar waste of time, which is exactly why we rely on Ground News, our partners at Ground News built an app and website that bring clarity to complex stories by showing how the world's media, from scientific sources and original research to political and international outlets, cover the same event. They were actually founded by a former NASA engineer with the same level of precision you'd expect for space missions. But the best part? Ground News isn't some new tool to learn. They're a smarter, better version of how you're already staying informed. If you're reading about this collider somewhere else, their browser extension flags bias and links you to dozens of science-focused, high-factuality articles instantly. We're giving our viewers 40% off the same unlimited access Vantage plan we use. Just go to groundnews.startalk or scan this QR code to bring the cost of context and clarity down to $5 a month. Be part of our mission to help the world understand the cosmos more clearly today. Now, back to the show.
So let's pick up some of the crumbs now.
All right.
So let's talk about his cosmological constant.
Okay.
What's up with that?
I love the cosmological constant. It's like the guy couldn't be wrong. It's like he couldn't be wrong even when he was terribly wrong.
Even when he was terribly wrong, he was right.
He was somehow later would turn out to be right.
Yeah, so one of the crumbs, a crumb you don't even know it's going to grow into an interesting
Right.
crumb later.
Right.
So your dog would need to give it a chance
Right.
before it laps it up.
He put it in his bed and he's saving it.
Yeah. I should go look up some more Einstein crumbs actually now that you're saying. Maybe this will give me some
I got to
invigorate
for yourself.
some,
Yeah.
some new ideas. Well, so Einstein writes down the general theory of relativity, which goes beyond special
This is
relativity.
later, 10 years later. Okay.
Yeah, it takes him. He
36. All right, now we're
he's
talking.
feeling it. He's feeling that there's something there that he wants to describe. Not just that space and time are relative. Not just that I can rotate space into time. That they're one kind of space time, but also that space time itself could maybe curve, stretch, be mutable, respond to matter and energy. That around the Earth, the reason why the apple falls from the tree is because it's following the natural curve in space, created by the mass of the Earth. This is general relativity now. He generalizes the theory away from flat space-time to curved space-time. Now, once he does this, he still cannot predict everything that this theory suggests. It's just abundant. It's so abundant that today people are still trying to find solutions from this theory to describe universes. And people came to him, a number of different scientists from around the world, very international experiment, and over very quickly and over the next couple of years said, your theory predicts that the universe is expanding. So other people are studying his theory. They're imagining, what if I have an average distribution of galaxies in there? All this stuff now, but I smooth it out. I imagine it's pretty smooth out there. And they say, how is space-time mutable in response to this distribution of energy? And you would sort of think, well, a lot of gravity means things are going to recollapse.
Yeah, everything has mass.
Everything has mass.
Right.
And so, it's all going to pull towards each other and it's going to cause a collapse of the universe, in which case the universe shouldn't be static, stable, or permanent. And Einstein really is resistant to this idea. He does not like it. And he says to himself, I must have made a mistake in my fundamental equations of general relativity that describe every possible scenario in the universe. And he had something called the cosmological constant, because technically, mathematically, it was consistent with Einstein's laws. And if you're being completely thorough, you would have included this term called this cosmological constant. And it's this magic term. Doesn't know what it is physically, doesn't know what it refers to in terms of known forms of matter.
So you can have a math
galaxies.
representation of an idea, not all of which actually applies to reality.
Yeah.
I
And
also like the idea that you
left
can
it
just
out.
like throw that in and be like, I don't know if my theory is right, but there's this magical extra thing.
Right.
And
He
now
knew-
it's right.
He knew it was mathematically consistent. That's
I
exactly
use it
what
on
he
my
did.
taxes. That's what I want to know.
That's exactly what he did.
Mathematically legit.
He said, look, maybe nature produces an energy density that's uniform across space and time, and it is an absolute constant, and it has this very different property that it actually pushes the universe outward, and if I tune it to exactly the right value, I'm going to balance things, and the universe will not collapse, and it will be permanent. And it will exist that way forever.
The universe is doing anything at all.
Right.
The
Doesn't
universe,
owe you anything.
It doesn't owe you, right,
Right.
right. The universe is just there. And if it's just there, you got to somehow stabilize it.
Yeah,
Yes.
so he stabilized the universe with the cosmological constant.
There you go.
Now he has a universe that's permanent, has lived forever, will last forever, but not so fast, because very quickly people study the mathematics of this and they say it's very unstable. You basically have stood a pencil on its tip on the top of a hill and said it's stable. I mean, you can do it for a second, but
If
it
that,
very
right,
quickly wants to fall over and begin to do something.
It'll fall in one direction or the other.
Or the other. And the two directions in this case, collapse or expansion.
Yes, there you go.
So either the universe is collapsing or it's expanding. It does not want to stay static. And he called it his greatest blunder. Now, he made a lot of kind of mathematical mistakes, so he was not afraid of that. And he was really so experimental and so daring. So the idea that he even called it a blunder, I think, was because it was a blunder of intuition
Wait.
or resistance.
Wait. It's not a blunder until it's a blunder. So he puts it in reluctantly, and then Hubble comes along
Telescope guy.
later in the.
Oh, that's true.
Yeah.
Telescope fame.
Yes.
Telescope came first. Yes. Edwin Hubble,
Yes.
comes along in the same decade, discovers that the universe is not static; it's expanding.
So now we're okay because that's one of the signs.
That's
of the hell.
one of the signs, and so
Right.
you don't even need the cosmological constant.
You don't even need the cosmological constant. So he comes along and says, look, the universe is not dominated by the cosmological constant from what he could measure. It's dominated by the galaxies, and the galaxies are, in fact, expanding away from each other. The universe is, in fact, expanding. And it was a real shock.
We had no physical way to understand a force or pressure in the universe going opposite gravity. There was no way.
And
then philosophically, what is it expanding into?
Yeah, I know. That's not right. We haven't gotten in.
We'll get there. Yeah. but at the time Einstein was first doing this, especially 1905, I mean, he didn't know there were other galaxies out there.
Oh, yeah.
I mean, imagine that.
Yeah.
We knew about the Milky Way, our little island of
The whole
hundreds
universe
of
was
billions
just the
of stars.
stars in the night sky.
And that was that.
Right.
I mean, he imagined, but it wasn't until Hubble that we identified that some of those objects out there really were, first of all, other galaxies, and that they were all moving away essentially on average, and that it looked like the universe was in fact expanding.
So at that point, he doesn't need the cosmological constant, and then he declares
His greatest blunder?
and then fast forward to 1998,
Right, and there it is.
and we discover the cosmological constant operating in the universe. It's measured, and it wins a Nobel Prize.
For him?
No!
God damn it.
Plus, they don't give it to you if you're dead. All right?
okay.
No, they don't announce
It might
that
have
you're a
happened
winner
once.
unless you're alive. But if you die between the announcement and the award ceremony,
then you're okay.
Then you're
You still
not
get the
alive.
award.
You're still dead.
But we gotta hold on. You gotta hold on till the announcement.
Yeah, if you die, you still get the award, but you're dead. All right. So in this sense, what
Yeah.
he rejects as a blunder
Yes.
becomes an actual measurement, and they get the Nobel Prize for making that measurement.
So now the reason why they can measure it, even though it's not static, you might think, oh, they could only measure it if it made the universe static or something. It actually was very unstable. What it really wants to do is kind of dominate. So as all the energy density in the universe kind of slowly wanes, this constant is eventually there to peak above all the others. As they dilute away, it just doesn't go away. And so eventually...
It's a permanent feature
it's a
of the vacuum
permanent
of space.
feature
It's crazy stuff.
of empty space.
Right. There's no way...
It is the energy of empty space.
Energy of empty space.
So eventually it will dominate the property of the universe. And what it does when it dominates is it drives the universe not only to expand, but to expand at an accelerated rate.
I've
It's
actually
getting
heard
faster and faster. Dark energy.
I've heard about the energy of empty space from my realtor.
Is that right?
They walk around, they say, you should feel there's nothing in here yet, but you should feel this energy.
Did they sell you air rights?
Right, exactly.
Maybe they should charge you extra for the dark energy
Yeah.
in the air rights.
Don't give them that idea.
And in 10 to the 22 years, which is a long time from now,
That's a pretty long time.
pretty long time, but I have it on my calendar, the dark energy will become so dominant and the expansion will become so accelerated that the fabric of space-time cannot keep up with it, and it will rip.
Well, that's not. You don't want to be alive then.
It's called the Big Rip. That's if it goes unchecked, the Big Rip. And
So if there are still humans that far out, they have to figure a way to
not
stop
have it rip. Right. It'll rip the very structure of the
like
fabric of space-time.
Cosmological climate change. Like they'll have, they'll have like...
Does it happen instantaneously, or do they feel it slowly start to happen, or is it like they just know at a certain
I
time?
know you
it's all
start
over?
seeing it all around you. Stuff starts flying apart. Oh yeah. Well, look, that face like is going to happen in your lifetime.
It's
So
my
now here's a good one.
great
Here's a
grandchildren's
good one.
problem.
Maybe you don't know this one.
Oh, yeah.
Okay?
Yeah.
He predicts, based on general relativity, that if you have an alignment of two objects, one of them will get lensed around it.
Oh.
And you get what is called an Einstein ring. Because if two objects are perfectly aligned together, the curvature of space will take that light and spread it into a perfect ring. And so you would see rings around
Right.
stars in the night sky from another star that's exactly aligned behind it. Here's the problem. Back then, the universe was composed only of stars. And stars are so small at those distances, you would never get an exact alignment. So he said this will probably never get observed until we discover whole galaxies out in the universe. And so it's no longer a point of light. The galaxy has a whole field. So there are many places you can be behind a galaxy and still have this phenomenon. So we see gravitational lenses all the time.
Yeah. And we see it around black holes. That's how we detected a black hole. We took a picture of a black hole because the light from behind it went above and below and cast the shadow of the black hole.
There's no above or below in space. Went around. You in my office. You're gonna,
Went around. Went around.
in my
She's out
office,
there in
I
space with a
can
compass.
see.
Like, what? It's all north.
so that was one that he predicted, assumed it would never be found. And then in my lifetime, like while I'm in graduate school, we discover gravitational lenses. Because people found these objects hanging off the side. I said, what is that? Why is it a little distorted?
A whole arc. And
It's a whole arc, and then
smear.
he took a spectrum of it and exactly matched the spectrum of the object on the other side, and that's the splitting of the light around the object. So that's another little crumb that fell off the dude's plate. Okay, so tell me about black holes themselves.
Yeah. Well, black holes also predicted from his mathematical theory, but
did he predict
But not by Einstein.
Why not?
He did not predict. Well, it's as I said, abundant. It's endlessly productive.
So black
You could
holes
sit
are
there-
crumbs.
Black holes
Yet to be shaped crumbs.
Yeah, you
Right,
have
right,
to
right.
go at the equations to decide what you want to think about.
Yeah.
Because it describes every possibility imaginable. Once you put matter and energy in, how will space and time curve? So how does that couch curve space-time? Not a great question. Scientifically,
That's
not
really
one most
not an
people
interesting
aren't going
question.
to spend their time on. But one guy decided, he's on the Russian front during World War I. Carl Schwarzschild.
Oh, Carl Schwarzschild, yes.
Yeah.
Did he die on the front?
He did. He died like 6 months after, I think, this
Okay.
correspondence with Einstein, where he sends him. He said, I found a very simple solution to your equations.
Did he die in the front because he was busy writing letters to Einstein?
I know,
Yeah.
but not paying attention to the bullets.
Hey,
So,
buddy,
yeah.
you're on the front.
Yeah. I think he contracted some infection. Oh. It was quite dire.
A lot of people back then died of
Yeah.
non-bullet injuries.
Related. Yeah. So, but he said, imagine, it was a thought experiment. Imagine you took all the mass of a star and you crushed it to a point. Or it could have been a planet, or it could have been anything. So you're imagining that all the mass is at the center and a point. You don't ask how nature would do such a thing. I don't even think Schwarzschild believed that there was a way nature would do such a thing. Certainly Einstein didn't. But the math was sound. It described the curvature of space-time if you're far away around a star or the Earth. But as you get closer and closer and all the mass is still in front of you, eventually you form this event horizon where not even light can escape. That's
Because
really what we mean by the
surface
black
gravity
hole.
gets higher and higher.
Yeah, it
and
just
higher.
gets, because the mass is always in front of you if you think about it.
Yeah.
Like if I go inside the sun, the gravity drops off because I'm leaving some of the mass behind.
No, you're vaporized.
I'm
but
vaporized.
Ignoring that complication.
Right. It's right. I always say, black holes are much more benign than people give them credit
Oh,
for.
yeah, you can
right?
just
the
dive-
star is incendiary, right?
Right,
but
right.
the black hole, you can get real close.
So this is
You just can't get out.
So we call this the Schwarzschild solution
Yes.
to Einstein's equations.
Yes.
So Schwarzschild does this.
Yes.
But he dies, so no Nobel Prize for him. But it's still an amazing result.
And Einstein
Right.
doesn't think they're real. He says it's beautiful. He helps get it published. And he couldn't believe that such a simple solution came out so quickly. It was within 6 months.
Or that
of
nature
the
would even
publication.
allow it.
Yes, he thought nature would not allow it.
Yeah, that there could be something that arises
Yeah.
that prevents such a catastrophic collapse.
Well, that makes
of
sense.
matter itself.
Right? I mean,
Just
try
staring
to
at the sky. No.
Well, try to crush a soda can. It's nearly impossible to get past a certain point. It's hard to do. It's hard to crush things because there's matter forces that resist.
Right, that's a soda can with soda in it. I could
Empty.
otherwise totally crush a soda can. Okay? Can I be
That'll
clear
be
about
like
this?
a demo that I want to see added, but only to a point. You can't make a black hole
No, not a black hole. Right.
because the atomic forces will resist.
Now, so I have to share this quick story with you. I'm having dinner with Stephen Hawking. And
Nice flex.
Yeah.
and so I was talking about Isaac Newton, where he did not figure out that the solar system was stable using his own equations. Okay? It turns out in the solar system, here's the sun, and here's like Earth going around. You're Jupiter. Every time I go between the sun and Jupiter,
You're saying I'm very big?
yeah,
exactly.
no, I'm saying you're gaseous.
I've been working to get to Mars.
I'm saying you're bulbous and gaseous. So Earth comes around, and it feels you a tug a little because you're closer here, right? And then over here, and it comes back around, it feels a little tug. So all these little tugs, he knew that if this continued, Earth would just fly out of its orbit. For thousands, millions of years, this would just be this runaway destabilizing force going on in the solar system. And so you know what he said? He said, God must step in and fix things.
Newton
Because
did.
that's how badass he is. He said, I know my equations
I can't
work.
do it.
Right.
So the only thing, because we see a stable solar system. Okay. But 100 years later, Laplace comes up with a formalism, a branch he develops with others, but he develops a branch of calculus that can demonstrate that these little tugs, which are multiple little tugs on a major system, all cancel out. It's called perturbation theory. But it's just a branch of calculus. The dude invented calculus.
Right.
Yeah.
So you can't figure that out. So I asked Hawking, I said, how come he didn't figure it out? Because who else are you going to ask if not Stephen Hawking?
Right.
So
And you waited a very, very long time for a reply.
yes, I did. Thank you. So I went on to other conversations,
Yes.
right?
Right.
And when he was
assembling-
ready-
Like I finished my entire meal.
with his eye blinks. He's assembling the answer.
Wow.
And it must have been 20 minutes. 20
yeah.
minutes later, he said something simple and brilliant. He said, you can't think of everything.
That took him 20 minutes to type?
No. You can't think of everything. And I said, that is so beautiful. And then he went on to say, to follow that with, Einstein did not come up with black holes.
That's right.
Because you
Yes.
can't think of everything.
Can't think of everything.
And I said, that's comforting, actually.
Yeah.
Right.
I mean, an entire industry of scientists have been since still working on Einstein's equations.
I got another one for you.
Okay.
He wrote a research paper on the stimulated emission of radiation. This is an extraordinary result that you have to kind of be on the inside to appreciate. Okay, I'll tell you what it is. You ready? So you have an atom with these energy levels where the electron hangs out. It's in discrete energy levels. It can't hang out anywhere. This is quantum. A quantum is units of anything. Okay? So it's quantized.
Even solace.
Quantum. Think about it if you have a quantum of solace.
Very Marquez somehow.
Yes, it is. So the electron can only be in any one of these discrete levels at any given time. And if it's at a higher level, left to itself, it'll want to de-excite back to a lower level. And it shoots out a photon in so doing. So this is what atoms just want to do. If you excite them, they want to de-excite. We got this.
Okay.
So let's go back to our atom, and we have an electron hanging out in an energy level. Now, I send in light, photons, that are exactly the energy level that'll boost this up. So it's going to absorb those and take them up. Okay? It's going to do that. However,
Oh, no.
here's what he discovers. That if you bathe an atom with an electron at a given level of photons that would boost it, it will also spontaneously trigger it to de-excite.
At the same time.
Yes!
Exciting and deep.
No. I mean, it will not, all the photons will not go to just boost it.
Gotcha.
Being in that bath will also de-excite it. There's no classical understanding of that. Okay? So it's the stimulated emission of radiation. Normally when you stimulate it, it absorbs it. This one, you shine on it, it de-excites. Okay, that's a weird result.
Yeah.
It's a quantum result that he deduces using math and quantum physics.
Yeah.
Okay? And what do we get out of this?
Well, we got lasers.
Lasers! You say that so calmly.
lasers.
We get lasers.
Einstein just
Pull your hair.
casually.
Pull some. Grab someone.
So it's really an interesting history because there were also masers before lasers, which were microwave versions of this. And Joe Weber, who wanted to study gravitational waves was working on masers, and they were completely overrun
So give
by
us
the
the
laser.
full acronym.
Microwave amplitude stimulated emission resonance or
I
something.
think laser stands for
You get a C- on that one.
Light.
I think laser
the-
stands for look and stare, experience regret.
Oh, very good on the spot.
Or it's like, remember George Costanza with the laser pointer? So it's like, look, a Seinfeld episode reference.
Oh, hey, this guy's good.
That's very good.
That's very good. From here on, let us call it.
Yeah. Well, yeah.
So the laser is an acronym like SCUBA and all these
Yeah.
fun acronyms.
Laser.
Light amplification
Amplification.
by the stimulated emission of radiation, and those are the three words
I did a real
in his
bad
paper.
job.
So light would be
You got the sir of laser.
So it'd be visible light, but it works with any kind of photons. Microwaves. It turns out it's easier to make a microwave laser. Microwave amplification by the stimulated emission of radiation. So this is just some paper he does like while he's taking a crap, all right? And publishes it, and then
His poop paper.
and then 30. I don't know if he was actually on
He was
the toilet.
experiencing some Brownian motion, if you will.
So Brownian movement, yes. So that for me, that's my favorite.
Is it
of
his crumbs?
Of his crumbs.
Interesting. I mean, it's an unbelievable technological advance. It's incredible. It's everywhere.
Yeah, because
Absolutely
the
everywhere.
amplification is if you emit light in this bath of light, and that light you emit is the same light when brought around that will de-excite it and emit a photon. So it's almost self-feeding. The light that it emits is the same light that it then absorbs. So this loop you can pump light that way with the right number of molecules in the right cavity. Oh my gosh.
And it becomes very coherent and very tight beam and very intense.
Yes.
So it's a way of getting like this incredible intensity at this one very narrow frequency range or light range.
Yeah. And so at the time, I'm sure he was saying to himself, skin peel.
Yeah.
Right. It's like, I'm going to hit a little laser.
Yeah, I mean, the application of laser were, oh my God. So the people who invented the laser, I think it was Charlie Towns, got a Nobel Prize for that.
Wow.
Yeah.
Did he expect it to be in like a Walmart?
Yeah, I know. At the checkout line.
Yeah, exactly.
Yeah, no, the first lasers were huge. And so just the idea that here's a paper that 30 years later becomes a device, and the device gets the Nobel Prize.
Incredible.
Do you know when Towns got the Nobel Prize?
So the laser was invented in 1956, 57, and Einstein died in 1955. So he would
was
not
so
have
close to seeing the laser.
So close. So close. And they were going to operate on him because he had some element
a
that
laser?
was... No. And he said, he was already in his 70s or something. He said, my work is done.
Did he really?
Yes. I thought that was classy.
Wow.
He was just scared of medical care.
Wow. I mean, he was still so combative with quantum mechanics.
Yeah,
I find it
give me the
fascinating.
quote.
Which one? The God does not play dice?
God does not play dice.
there are others.
Was it Niels Bohr who said back to him, another physicist, Einstein, stop telling God what to do? It was one of several times he talked about God and God's intentions because quantum physics is fundamentally statistical. It's does not describe a unique objective reality. It only describes a statistical reality. And this felt very bad to Einstein, even though he made significant contributions to quantum physics.
This feels like a trend, though, because Newton also was like, I don't know, God.
Yeah, bring a God when you need him. So a couple of fast other ones. So he predicts out of general relativity that certain phenomena should produce ripples in space-time continuum, gravitational waves.
Right, gravitational waves. So he says, look, if the Earth can curve space-time, if the sun can curve space-time so that the Earth falls around the sun, then if these systems move around, the curves have to move too. So the curves themselves have to modulate like waves. And he predicted something called gravitational waves, which are these silent waves in the shape of space-time. And they are not visible. It's not light. It's pure gravity. It's not light. But if you saw something, you could see it bobbing on the wave as its path changed around a moving object. So if the sun decides to, do something crazy, we would know 8 minutes later when the wave got to us.
So I think I have this right. There's a cottage industry rising up in astrophysics where they're looking at the pulsars in the galaxy. Pulsars are very fast rotating stars that have extremely precise timing. Precise. So, if there's a gravitational wave not coming towards us, but passing across our field of view, we can see the effect of the turbulent space-time wave on the timing of the pulsar as it goes through the wave. And then you can see them move across the universe.
They'll bobble around. They're like buoys on the ocean.
Yes, you'll see this effect as that happens. And so it's like, whoa. So
now, he wrote many papers where he thought they didn't exist. So
Einstein,
he really
the
struggled
idiot.
with whether or not these.
Really hedging his bets there.
I know, right?
I don't know if black holes exist, but maybe.
Well, gravitational waves were really confounding, whether they carried energy or were real in a substantive way, or was just, I'm just changing my coordinates. It's not physically real. There's no physical impact. This was confounding for decades. He once would write, he wrote papers where he said they do not exist, they would be accepted for publication, and in the space between publication and sending it to press, he would change the entire paper and say they do exist.
In the space between it being accepted
Yes,
and
between
going
it
into
being
print.
accepted and going into print, he would change the entire conclusion, rewrite the paper,
Right,
and
he's
say they
hedging
do
his bets.
exist.
Yeah.
He wants to be right no
He
matter
published
what.
both papers.
Right. So then we decide maybe we can detect some of these. And Kip Thorne, who was a guest on our show, we took StarTalk to him because he's Kip Thorne.
Right.
Yeah, we moved the mountain to Kip Thorne. We went to his home office in Pasadena. He's a
Nice.
professor at emeritus now, I think,
Yeah,
at
Caltech.
And we talked about Interstellar because he was a executive producer on Interstellar.
He wrote the original treatment. It
He
was like
did.
his dream idea.
He did
Yeah.
write the original treatment. He brought on Christopher Nolan to realize those views. It wasn't the other way around. So he petitions Congress and the National Science Foundation and other agencies and with a lot of support from other physicists and the like,
Ray Weiss,
to build the first gravitational wave detector. And it's built, it's called LIGO, Laser Interferometer Gravitational Observatory, LIGO, sensibly abbreviated LIGO. And they made it really sensitive to this. They have two lasers that go off at right angles, and if a wave washes over Earth, the length of one laser path will change relative to the other. They make this measurement. Bada bing! They found the first colliding black holes, which deposited so much energy into the space-time continuum that we'd have a chance of measuring it.
Yeah. I mean, it was the most powerful event humanity's ever observed since the observation of the Big Bang itself. More
But it was
energy
all-
came out of this.
All in
Right.
gravitational waves.
In utter darkness.
Utter darkness.
And yet, that the power was greater than all the stars in the observable universe combined at that moment. So, but it all came out just in ringing space, literally. So darkness.
Right.
Could not see it with a telescope.
And so, think about it.
I love the look on your face. Thank you for that.
He's looking back and forth like, whoa.
I'm trying to think of anything else that would be more powerful than those stars combining. But I'm stuck at Taylor Swift and Travis Kelce. When those stars came together,
That was a
we
moment.
all felt it.
That was a moment. It was a tectonic shift. So, we discover gravitational waves. That won a Nobel Prize. But more so, we discover gravitational waves using lasers. Okay.
His crumbs connected.
His crumbs came together and made a big smorgasbord of science and physics and Nobel Prizes for everybody on board. So, can you get more amazing than that? I mean,
The detection was essentially in the centenary, too.
Yes, it was in
Einstein's
2015.
papers
100 years.
of
In
100 years
2015.
after his gravitational wave papers.
Oh man,
Yeah.
that's Einstein has
I
something
mean,
to do
he's
with that.
magic.
Einstein totally had something to do with that. Now, Janna, memory serves, Einstein was a big proponent of a unified field theory. And when I first heard that when I was a kid, field? What do you mean by field? I didn't know that field was synonymous with forces, right? So we have gravitational force, electromagnetic force, which in its day was the electric force and the magnetic force.
And then the Force.
And
I've seen Star Wars.
maybe they figured it out. They got the one force, you know. So with the work of Heinrich Hertz and others, we figured out how to combine electricity and magnetism to make one force. And we take that word for granted, but they used to be two whole separate words. Electromagnetic force. So Einstein why did he fail at this? Or what was motivating him?
Well, we've all failed at this. So,
Okay.
so there's great success in unifying all of the matter forces, all of the quantum matter forces, electromagnetism with the weak nuclear force and the strong nuclear force. That's the whole story of matter. Done. Completely sealed.
Yeah, but they're not
There's
combined.
an outlier. Well, so the electroweak theory is combined. Weak
Right.
and
So we went
electromagnetic.
from electricity, magnetism, and the weak nuclear force.
Right.
Then we got electromagnetism, and then with my guy from my high school.
Right. Which guy from your high school?
What? Steve Weinberg and Sheldon Glashow.
Yeah.
They and
What was
who's
this high school?
the,
Oh, no, yeah.
Who's
No,
the third
maybe-
one in there?
Salam. Abdul
Abdul Salam. Right,
Yes.
that's correct. So the three of them, two of them were classmates in my high school before me, but in my high school. Anyhow,
There was something in the water there.
they
for sure.
managed to conjoin the electromagnetic force and the weak force, and they called it what?
Electroweak.
Okay, that's not very creative, but all right, we'll go with it.
But it is pretty magical. It says that those are really one force, which is magical. Something that is at nuclear ranges that we do
That's
not experience in our
manifesting
everyday
as
life.
separate forces
Yeah.
today.
Right.
You go back in time.
Right.
There's a point where they were just one expressed force in the universe. So that gives us electroweak, strong force, and gravitation.
Yeah. Now the strong easily can get in there, even though we don't talk about it very much anymore.
What do you mean easily? If you did that,
Easily.
you'd have a Nobel Prize now. So
Well, there's something called the grand unified theories, and they have certain failures. There isn't like an ideal grand unified theory, but really, there's nothing barring the possibility of it. I mean, it's
no
not
obvious obstacle.
There's no fundamental obstacle to a grand unified theory. Most people think it's going to come along for the ride when we do the full unification.
So when Einstein said a unified field theory, was he thinking just that, or was he also want to include gravity?
He wants gravity.
He wants gravity.
He wants gravity. And it's the same thing he did when he went from special to general. When he started thinking about quantum mechanics, he wants a quantum theory
But
of
gravity
gravity.
behaves so differently from the other forces. Because you can think of gravity not even as a force, but as the just falling down the curvature of space and time.
That's geometry.
It's geometry. It's not really a force. So that could be a barrier to summing these together.
Well, nobody's ever succeeded at even.
So how about Kip Thorne? Does he have some ideas here? Does he?
Oh well, I mean, Kip has endless ideas.
Yeah, he does.
And
He does.
I think
Interstellar 2.
Yes. I think Kip's ambition is for, yes, a universe that would be completely comprehensible, which would mean we either understand quantum gravity or we understand that gravity is not fundamental. Those are the two kind of choices.
Oh, yeah,
That
so-
everything's quantum mechanics. Now, I don't know that
quantum
Kip's...
mechanics is the most successful idea we've ever had about anything in the universe. I don't think any prediction has ever failed.
No, and to the largest number of decimal points of any scientific theory in the history of
Right.
time.
Whereas general relativity, as badass as it is, we know where its limits are. Like at the center of a black hole is a singularity. It gives you a singularity in the equations. And I don't know what, that's what they say, where God is dividing by zero.
Right.
Remember, you're not supposed to divide by zero? Yes. Bad.
Well, even
Right.
Roger Penrose, who talked about the singularity in
Roger
his
Penrose,
Nobel Prize winning
Nobel
paper,
laureate of recent years.
even in that paper, he says, I don't really think this part's going to survive. He really says, quantum mechanics will probably get rid of the singularity. But it hasn't done any of the things it was supposed to do around gravity. So
Point is, more crumbs
more crumbs.
await
Yes.
the attention of brilliant people.
Yes.
Either who
Wormholes.
walk among us or are yet to be born.
I'm just going to throw in, because this is very relevant to this, wormholes, which Einstein talked about, the Einstein-Rosen bridges,
Okay.
which ultimately give rise to wormholes, might be involved in understanding that things like black holes and gravity aren't fundamentally real. They're just sort of embroidered out of quantum wormholes. And so it might really be another one of Einstein's
Yeah, sound
crumbs.
embroidered out of quantum wormholes.
And not
Like
real.
threads. So more crumbs from Einstein to come.
Wow. Is there
Keep your eyes on wormholes.
Is there any other scientist that is that a messian eater, so to speak? Has anybody else left?
No, Isaac
crumbs?
Newton was badass too.
Okay.
In fact, I think if Isaac Newton were a contemporary of Einstein, he would have done everything Einstein did and more.
Whoa.
I'm a Newton guy.
Okay.
Yeah, you're a real Newton guy.
Yeah, you got to give me something here.
Yeah.
I'm a Newton guy.
I mean, calculus is pretty impressive.
That's pretty good.
Yeah, just like on a dare. It's like, Isaac, why are your orbits moving in ellipses rather than circles? He said, well, I don't know. Let me get back to you on that.
I'm gonna eat an apple.
Yeah.
Let me go back. And well, here's why. And well, how did you do that? Well, I had to invent integral and differential calculus to show that. Okay, Isaac. So if you'll indulge me just for a moment, I need to reflect on our conversation. Love me some mathematics. Why? It was early on when I learned, when I wanted to be an astrophysicist, that the language of the universe is mathematics. Now, that's an extraordinary fact because we just invented mathematics out of our heads. The history of math is filled with examples of, I don't know how that works. Let me invent a way to calculate with it so that I can figure out how it works. Thus is the rise of arithmetic and algebra and trigonometry and calculus. All of this helps us commune with the cosmos. But what makes it even more extraordinary is you start out with an idea of how the universe works, but you can't manipulate that idea because you're stuck with using only words. If you make a mathematical representation of that idea, then you can manipulate that idea using the perfect logic of mathematics. And by doing so, you can extend the idea in places you didn't even know the idea could go, because you're extending it with perfectly logical steps from the map of that idea into the world of mathematics. The fact that that works for us at all leaves me in awe of not only the existence of mathematics, but of the human mind that took us there. And here we have, in the likes of Albert Einstein, laying down a physical idea of how the universe works, attaching a mathematical model to it, and the rest of us run with that mathematical model. Crumbs from Einstein's plate, leading to Nobel Prizes that at some level should have all gone to him. My boy should have had 8, 9, 10 Nobel Prizes. But he's sharing his genius with the rest of us in these, the 20th and 21st centuries. More to come from Einstein's Crumbs. And that is a cosmic perspective. So, Janna, thank you for helping out here.
Thanks, I'm always glad to be here.
And you have a podcast. Tell me.
Oh, right. Joy of Why.
I love that.
Oh, yeah.
The Joy of Why.
So,
that's a beautiful title.
Yeah, Quantum Magazine. So the story is my friend Steve Strogatz, who's the original host of the show. It's by Quantum Magazine from the Simons Foundation. Wonderful science magazine. His book was called The Joy of X. Mathematician, and I thought that was a brilliant title. And so the show was originally called Joy of X.
Called The Joy of Lex, which is all about language and words.
There's another one I think called The Joy of Sex.
Yeah, that started it all. Yes, okay. Yeah.
Yes, that was the original. So Steve and I co-host a show. It's a lot of fun. We deep dive hardcore physics,
Excellent.
biology, computer science.
Good. And the Simons Foundation
Math.
From Jim Simons, the
Yes.
very successful
Yes.
Wall Street trader. I think he's the most
Heroic
successful
Jim Simons.
Wall Street trader there ever was. And
He's the
brought
original quant.
His background in math and physics.
A brilliant
into that.
mathematician and an accomplished mathematician. Like we still use his mathematical results in theoretical
I
physics.
took it right on his yacht. And it was called the Archimedes.
Nice.
That's classy.
Jim was the best.
All right, I think we did justice to Newton's Crumbs here. Oh
Thanks
my gosh.
so much, guys. Always fun.
Yeah, thanks for filling in those gaps
Yeah.
and taking us to the next step. And Harrison, you're on the road with your routine.
Yes, I have my comedy magic show. We've been off Broadway. I'm taking it on the road, and I'm doing stand up all over the country.
And
HarrisonGreenbaum.com.
.com. We'll look for it. All right. This has been StarTalk, the Einstein Crumbs edition. Neil deGrasse Tyson here. As always, I bid you to keep looking up.